Hello. So we just finished Unit 1. So in Unit 1, we talked about collecting data, and then we talked about summarizing data with graphs, and then summarizing data with numbers, such as mean, median, and standard deviation. In Unit 2, we're going to start talking about probability. And this is going to be the link between the first unit and the third part of our course, where we talk about drawing conclusions from data. So back in Unit 1 at the beginning, I gave you this example of deciding whether a medicine or a vaccine works. So what do? You take two groups of people, right? One group you give the medicine to, the other group you give a placebo or a fake medicine to, and then you measure something and you see if there's a difference. Now, the hard part is these are two different groups of people, so you expect there to be a difference anyway. And the question is, when is that difference big enough for it to matter? So in the language of statistics, when is that difference big enough to be significant? And when is that difference so small that it could have been due to the fact that we just have two different groups of people? And probability is going to be the tool that helps us decide between those two possibilities. All right, so let's talk about some terminology. A probability experiment. So a probability experiment is just any process where you don't know what's going to happen. So it's a process where the individual outcomes are unknown. Okay, so for example, this is a dice. It's a 12-sided dice. So when I roll this dice, I don't know what's going to happen. We got a 9. Okay, so an example would be a 12-sided dice. Other typical examples are flipping a coin, shuffling a deck of cards, and pulling out a random card. For statistics, the main example that we're going to talk about is we have a population of people, and I'm going to select a sample of 100 people. So I'm doing this randomly, so I don't know which 100 people is going to get selected. Right? So that's the main example for statistics. Sample space. So even though I don't know what's going to happen when I roll this dice, I do know what could happen. Right? So for a sample space is a list of all the possible outcomes. Right? So in our case, with the 12-sided dice, right? So even though when I roll this, I don't know what's going to happen, I do know that because it's a 12-sided dice, I could get a 1, a 2, a 3, a 4, a 5, a 6, all the way up to 12, right? So a list of everything that could happen would be, so S for sample space, 1, 2, 3, all the way up to 12. An event. Okay, so when I talk about an event, right, I could talk about, what's the probability that I get a 6 when I roll this dice. But I could also talk about things like rolling a multiple of 3. Right, so when we say a multiple of 3, it could mean a 3, it could mean a 6, it could mean a 9, it could mean a 12, right? So it's not a single number, it's a collection of numbers. So when I say multiple of 3, it's not a single number out of this sample space, it's the numbers 3, 6, 9, 12. So an event is just a sub-collection of the sample space. Probability. So probability is a measure of how likely something is to happen. And you've seen this before. So on the news, you may hear there's a 60% chance of rain on Saturday. Or you may hear your chance of winning the lottery is 1 out of 300 million. Okay, so those are probabilities. They can be percents, they can be fractions, they can be decimals. But they're numbers that are between, or decimals that are between 0 and 1. Right? As a percent, 0 is 0%. 1 as a percent is 100%. Most of the time for this class, we'll talk about probability using decimals. So a probability of 1, what does that mean? So if something has a 100% chance of happening, what does that mean? It means that it's always going to happen. And if something has a 0% chance of happening, that means it's never going to happen. So how do you actually calculate probabilities? So there's two approaches, classical probability and empirical probability. In the classical probability approach, we're going to count. So we're going to count how many outcomes are in the sample space and how many outcomes are in the event that we're interested in. Okay. So on the bottom, we're going to count the number of outcomes in the sample space. And then on top, the number of outcomes in the event E. Okay, so let's go to our example of the 12-sided dice and the event of rolling a multiple of 3. Right, what's the probability that we get a multiple of 3 when I roll this dice? Right, so the way you calculate it using the classical approach is you count. So for the bottom, we'll count the number of outcomes in the sample space. Right, we listed out our sample space up here. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 things in the sample space. So that's on the bottom. The event E, multiples of 3, we also listed. So count 1, 2, 3, 4. There's 4 things in the event E. So the probability is 4 out of 12, which as a decimal, 4 divided by 12 is 0.333. Okay, that's the probability of getting a multiple of 3 when I roll this dice, right? Usually when we talk about this to the general public, we convert this to a percent. So this as a percent would be 33.3%. Right, so to someone who doesn't know statistics, we say there's a 33.3% chance of getting a multiple of 3 when I roll this dice. The empirical approach, you actually do the experiment, right? So you do the experiment. And then you count the number of times that the event happened. Okay, and the calculation is going to be, okay, on top is the number of times the event happens. And then on the bottom, the number of times you did the experiment. Number of times experiment was done. Okay, so let's do the experimental probability of getting a multiple of 3. All right, so instead of counting sample spaces and events, I'm actually going to roll the dice. I'm going to roll it 6 times, and then count how many times I get a multiple of 3. All right, so let's Right, so I know ahead of time, I'm telling you, I'm going to do this 6 times. I'm going to roll this dice 6 times, and we're going to count how many times we get a multiple of 3. Okay? That's 1. That's not a multiple of 3. That's not a multiple of 3. Not a multiple of 3. That's not a multiple of 3. That's not a multiple of 3. And I think I roll one more time. Got 12. So that is a multiple of 3. So I rolled it 6 times, and a multiple of 3 happened 1 time. So the experimental probability is 1 out of 6, which as a decimal is 0.167. Which as a percent is 16.7%. Example 1, a coin is tossed 4 times. So when I toss a coin 4 times, I don't know what's going to happen, right? But I can list out everything that could happen. And that's what we're going to do in part A. So part A says construct a sample space for this experiment. So just list out everything that could happen. So the way I want to think about this is as 4 separate coins. So here I have 4 coins, a penny, a dime, a nickel, and a quarter, right? Right now it's heads, tails, heads, heads. And the reason why I want to think about this as 4 separate coins is I want to distinguish heads, tails, heads, heads as different from tails, heads, 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 right? So in both of those cases, we have a single tail and 3 heads, but I'm going to consider those as separate, okay? So with that in mind, let's list out all the things that could happen. So I think the best way to organize this is to think about how many heads you have. So what are all the possible ways you can get 0 heads? Well, there's only one way you can get 0 heads, right? If all of them are tails, right? So the only way you can get 0 heads is if it is tails, 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 tails. Okay, I think that's all. So move on to the next one, which would be 1 head. So what are all the possible ways you can get 1 heads? So one of them would be heads, tails, tails, tails. What's another way? Tails, heads, tails, tails. Right, so I'm just moving those heads into different spots, right? So at the first spot, second spot. Another one would be tails, tails, heads, tails. Another one would be tails, 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 heads, right? So I'm just moving the heads in the first slot to the second slot to the third slot to the fourth slot. Okay, is there another way I can get 1 head? I don't think so. Okay, so once you've decided that you're done, move on to the next one, which would be 2 heads. Okay, this is a little bit harder. So list out all the ways you can get 2 heads. So one way would be heads, heads, tails, tails. Okay. I can also flip that, so that would be tails, tails, heads, heads. What's another way? Well, I can alternate, right? So I can go heads, tails, heads, tails. I can flip that, so that would be tails, heads, tails, heads. Is that all? Is there another way you can get 2 heads? Yes, you can, right? So you can have the 2 heads in the middle, so that'd be tails, heads, heads, tails. And then if you flip that, that would be heads, tails, tails, heads. And then, is that all? So think very carefully. Can you think of another way that you can get 2 heads? I can't. So I think I'm done here. So I'm done with 2 heads. Next up will be 3 heads. Okay, what's all the possible ways you can get 3 heads? So you can get heads, 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 tails. What's another way? So this should be similar to the 1 head situation, right? Because this is really just 1 tail. So I'm just going to move the tails to different locations, right? So right now it's in the last spot. I'm going to move it to the 3rd spot. So that'll be heads, heads, tails, heads. And then I'm going to move it to the 2nd slot. That'll be heads, tails, heads, heads. and then I'll move it to the front slot. That'll be tails, heads, heads, heads. And that should be all of it, because it should be the same as the one head. Okay, because this is really just one tail. Okay, so then move on to the next one will be 4 heads. And this one's easy. There's only one way you can get 4 heads, which would be all of them heads. And I think that's all. Okay, so there's a hint here that says that there should be 16 outcomes. So let's make sure. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, good. We got them all. Okay, so now to answer the questions, what's the probability that there are exactly 3 heads? Okay, the bottom number is going to be all of the possible outcomes in our sample space, which we counted. There's 16 outcomes in our sample space. And then for the top, we just count. How many have exactly 3 heads? So exactly 3 heads would be these, 1, 2, 3, 4. Okay, so 4 out of 16. Okay, 4 out of 16 as a decimal would be 0.25. Okay, which as a percent would be 25%. Okay, so for this class, I know you know how to convert to a decimal and a percent, so we're not going to do that. You can leave all your answers as fractions. Okay, so for the lab, leave it as 4 over 16. You don't have to simplify the fractions either. Part C, what's the probability that there are at least 2 heads? Okay, so bottom should be the same, right? It should be all of the, however many are in the sample space, so there are 16. And then count how many have at least 2 heads. So what does at least 2 heads mean? What does at least 2 mean? So at least 2 means 2 or more, right? So when I say you have to be at least 21 to buy alcohol, right, that means 21 or over, right? So at least 2 means 2 or more. So how many of these have 2 or more heads? So that means all of these, right? 1, 2, 3, 4, 5, 6. And also these. That's 6, 7, 8, 9, 10, 11. So there's 11 with at least 2 heads. Part D, what's the probability that there are more than 2 heads? Right, so bottom number is still 16. More than 2. So more than 2, we're not counting 2, right? More than 2 means 3 or more. So that's these and these. So that's 1, 2, 3, 4, 5. And finally, what's the probability that the first and last tosses are the same? Okay, bottom is still the same. It's still 16, the total number of outcomes in the sample space. And then we're going to count. How many of them have the first and last toss the same? 1, 2, 3, 4, 5, 6, 7, 8. I think that's it. Okay, these are all the ones where the first and last are the same. So I think there's 8 of them. So 8 out of 16 for part E. Example 2. So here we're rolling 2 6-sided dice. All right, so when I roll 2 6-sided dice, I don't know what I'm going to get, but I can list out everything that I could get. Right, so which is part A, construct a sample space. I'm going to think of this as 2 different colored dice, and the reason why is because I want to separate 2 on red, 5 on blue as different from 5 on red and 2 on blue. Okay, I'm going to count those as different outcomes. Okay, so whenever we have just 2 things, the easiest way to list out all of the possible things that can happen is to make a table. So along the vertical, I'm going to list out all the possible things that can happen on my first dice. So this is a 6-sided dice, so I could get a 1, 2, 3, 4, 5, or 6. Okay, so this is my first dice. And in this case, it's the red one. And then along the horizontal, the top, I'm going to list what could happen on my other dice. Okay, so it's also a 6-sided dice, so I could get a 1, 2, 3, 4, 5, 6 also. Okay, and this is my second dice. In this case, it's the blue one. Okay. All right, so what I care about is the inside of the table, not the numbers on the outside. So let me actually separate those out. Okay, so it's the boxes on the inside that represent what could happen. What do I mean by this? So for example, this box right here represents getting a 2 on the first dice and a 6 on the second dice. Right, a 2 on the first dice and a 6 on the second dice. This box, let's say this box here, represents getting a 4 on the first dice and a 3 on the second dice. Okay, let's do one more. Say this one here, 1 on the first dice and a 3 on the second dice. All right. So the inside represents everything that could happen when I roll 2 dice. Now, if I go to my questions here, I'm asking about what's the probability that the larger number is 4, what's the probability that the larger number is less than 6, what's the probability that the larger number is at least 5. Okay, so what I care about here are the larger number. Okay, so I'm going to actually, inside the boxes, I'm going to list the larger number. Okay, so for example, here is getting a 2 on the first dice, a 6 on the second dice. So the larger number would be 6. Okay, that's the number I care about. Here, 1 on the first dice, 3 on the second dice. So the larger number will be 3. Here, 4 on the first dice, 3 on the second dice. The larger number would be 4. Okay, I'm going to go through and list out the larger number in each case. So here, 1 and a 1, larger number is 1. Here, 1 and a 2, larger number will be 2. Here, 1 and a 4, larger number is 4. Okay, so in each case, for each box, right, I looked at the first dice, second dice, and then I just listed the larger number, right? So these are the larger number. Okay, and I'm putting the larger number because I'm asking about the larger number here. All right, so now to answer the questions. What's the probability that the larger number is a 4? Okay, so bottom number is going to be everything that could happen when I roll 2 dice. So everything that could happen is represented by these boxes on the inside. How many boxes do I have? 1, 2, 3, 4, 5, 6. And then there's 1, 2, 3, 4, 5, 6 rows. So that's 36 total. So these are the red numbers. And then how many of them are the larger number is 4? So in how many boxes is the larger number 4? So that's, let's see, 1, 2, 3, 4, 5, 6, 7. Right? So remember, we're not counting these numbers on the outside. We're just counting the numbers, these red numbers on the inside. So there's 7 out of 36. Part C. Okay, bottom number is still going to be 36. What's the probability that the larger number is less than 6? Right? So we're looking at the red numbers here. So how many of them are less than 6? So less than 6 means don't count 6, right? So it's It's 5, these 5s, these 4, these 3s, these 2s, and these 1s. So that's actually a lot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. 25. Part D, what's the probability that the larger number is at least 5? Bottom number is still the same. At least 5, remember the word at least means 5 or more. Right, so I want these 5s and then these 6s. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Example 3. A 4-sided die and a 6-sided die are rolled. Right, so here's a 4-sided die, here's a 6-sided die. Right, so when I roll it, I don't know what's going to happen, but I can list out everything that could happen, right? Which is what part A is asking. Construct a sample space. Because I have only 2 things, right? The easiest way for me to list out what could happen when I have 2 things is just to make a table. Okay, so on the left side, I'm going to list what could happen on the 4-sided die. So when I roll a 4-sided die, I could get a 1, 2, 3, or 4. And so this is my 4-sided. And then along the top, I'm going to list out all the things that can happen on the 6-sided die. So for a 6-sided die, I can get a 1 through 6. Okay, so this is my 6-sided die. And by the way, we couldn't do a table for the first example with the coins because we were talking about 4 coins, right? Which is 4 things. So you can't do a table if you have more than 2 things, right? Because there's only 2 sides, a vertical side and a horizontal side. Okay, and what I care about are the boxes on the inside, not these numbers on the outside. Let me separate those out. Okay, so the boxes on the inside represent what could happen, right? So for example, this box represents getting a 2 on the 4-sided and a 6 on the 6-sided. This box represents getting, let's actually talk about this box. This represents getting a 3 on the 4-sided and a 4 on a 6-sided. This box here represents getting a 4 on the 4-sided and a 2 on the 6-sided. Okay? All right, so if I look at my questions here, it's asking what's the probability that the sum is 5? Part C, what's the probability that the sum is more than 7? Part D, what's the probability that the sum is at most 3? Okay, so what that tells me is that what I should put in the boxes is the sum, right? Which means add up the 2 dice, right? So here, I get a 2 and a 6, the sum will be 8. Here, a 3 and a 4, the sum would be 7, so add them up. 4 and a 2, the sum would be 6. Now notice that this differs from what we did in example 2. So in example 2, I didn't put the sum, right? In example 2, I put the larger number in there, right? A 2 and a 6, the larger number will be 6. And why? Because part B, C, and D, we're asking about the larger number, right? Larger number, larger number, larger number. So here, the questions are asking about the sum, so I should put the sum in there, okay? So let me go through and put in the sum. So a 1 and a 1 will be a 2. Here, 1 and 2 will be 3. 1 and a 3 will be 4. 1 and a 4, 5, 6, 7. 2 and a 1 is 3. 2 and a 2 is 4. 2 and a 3 is 5. 2 and 6, or 2 and 4 is 6. 2 and a 5 is 7. That's a 4. That's a 5. That's a 6. 8, 9, 5, 7, 8, 9, and a 10, right? So all I did was, for each box, I looked at what the 2 dice were, and then I added those numbers. Now, part B. What's the probability that the sum is 5? Okay, for the bottom, you're going to count all of the things that could happen in the sample space. So this is represented by the boxes on the inside. So there's 1, 2, 3, 4, 5, 6. And then there's 1, 2, 3, 4 rows. So that's 24. 6 times 4 is 24. So there's 24 boxes on the inside. And then how many of them are 5s? 1, 2, 3, 4. Okay, remember, we're just counting what's on the inside of the box, not the numbers on the outside. So just the red numbers in this case. Part C, what's the probability that the sum of the dice is more than 7? So bottom is still 24. More than 7, so more than 7 means you don't include 7. So these will be 8s, 9s, and 10s. So 1, 2, 3, 4, 5, 6. Part D, what's the probability that the sum is at most 3? Okay, so we haven't heard that phrase at most yet. We've heard at least 3, right? So at least 3 means 3 or more. At most 3 means that the biggest it can be is 3, which is the same thing as saying 3 or less. Okay, at most 3 means 3 or less. So the bottom is going to be 24. 3 or less means 3s, 2s. So that would be just 1, 2, 3. Example 4. Roll a 4-sided die and a 6-sided die and record the sum. Notice that in example 3, the previous one, I was also talking about a 4-sided die and a 6-sided die, and I was also talking about the sum. Right? We asked, what's the probability that the sum is 5? What's the probability that the sum is more than 7? What's the probability that the sum is at most 3? Now, we found these probabilities by not rolling any dice. We didn't roll any dice, right? We just thought about what could happen, right? We made a sample space, and then we counted. So that's called the classical or the theoretical probability, right? We found the answers by not actually doing the experiment. We found the answer by thinking about all of the things that could happen, and then we counted. So in example 4, I'm asking for the empirical probabilities, right? So now I want the probabilities from actually doing the experiment. And what I want to do here is just compare the answers, right? And see what we get. So we're going to roll a 4-sided and a 6-sided, right? And then we're going to add up the numbers. So I'm going to list out all the answers I could get, right? So the smallest number I could get is if I get a 1 on the 6-sided and a 1 on the 4-sided. So add those up, that would be a 2. What's the biggest number I can get? On the 4-sided, the biggest I can get is 4. On the 6-sided, the biggest I can get is a 6. If I add those up, that's a 10. And then I can also get all the numbers in between, right? So I can get a 3, 4, 5, 6, 7, 8, 9, and a 10. Okay, so what I'm going to do here is I'm going to roll a dice, add up the numbers, and then make a note of it in my table. All right, so here's a 6 and a 2. That's an 8. This is a 3 and a 4. That's a 7. Right, so I'm going to do this many, many times. And I actually did this already over the weekend. I did it a lot of times. And let me tell you what I got. So here's what I got. I got a 2, 251 times. I got a 3, 494 times. I got a 4, 720 times. I got a 5, 954 times. I got a 6, 952 times. I got a 7, 960 times. I got an 8, 751 times. A 9, 493 times. And a 10, 239 times. Okay, I spent my weekend rolling dice. Okay, a lot of times. Now, part A. What's the empirical probability that the sum of the dice is 5? Okay, so for empirical probability, okay, on the bottom, you put the number of times you did the experiment. So the number of times I rolled dice. So how many times did I roll dice total? Well, add up these, right? Okay, so 251 plus 494 plus 720 plus 954 plus 952 plus 960 plus 751 plus 493 plus 239. Okay, total 5814. All right, so I rolled dice 5,814 times. Oh man. Okay, so that's the numbers that's at the bottom. Okay, number at the top is number of times the event happened. So what we're talking about here is number of time I got an answer of 5. So how many times did I get a 5? 954 times. Right? So 954 times I got a 5. And then out of 5,814, that's the total times I rolled dice. So this 954, I'm actually going to divide here. 954 divided by 5814. And the reason I'm dividing here is because I want to compare it to the answer in example 3. So here the answer is 0.164. Okay, part B. What's the probability that the sum of the dice is more than 7? Okay, so bottom number is still going to be 5814, the number of times I did the experiment. More than 7 refers to 8, 9, and 10, right? So I'm going to add up 751, 493, and 239. 751, 493, 239. Okay, and that's 1483. Okay, and then if I divide, what do I get? 1483 divided by 5814. 0.255. Part C, what's the probability that the sum is at most 3? Okay, bottom still the same. At most 3, remember, means 3 or less. Okay, so 3 or less means 3 and below, so that's just the 3 and the 2, so that's 494 plus 251. Okay, that's 745. If I divide 745 divided by 5814, 0.128. Okay, so now I'm curious. So these are answers I get by actually rolling dice many times, right? 5,814 times. Compare that to the answers I got in example 3 by not rolling any dice, but from just thinking about all the things that could happen, right? So the answer from, I'll compare here to so let me do these in red. So for part B, it was 4 out of 24. Part C, it was 6 out of 24. And then the third answer was 3 out of 24. Right, so let me actually calculate and see how close or how far away these are. So 4 out of 24, 0.167. 6 out of 24, 0.25. 3 out of 24, 0.125. So these are the numbers I got. These are probabilities I got from doing it theoretically. So theoretical probability from just thinking about what could happen and thinking about and counting from there, versus the numbers I got from actually rolling the dice, right? So notice they're actually about the same, right? 164, 167, 255, 25. That's actually, it means 250, right? So about the same. 128, 125. about the same. Okay, and that's the point of what's on the next page. The law of large numbers is basically what we just saw on the previous page. So it says that the experimental probability and the theoretical probability are about the same, assuming that you're doing the experiment many, many times. So as we repeat the experiment many, many times, the experimental probability gets closer and closer to the theoretical probability. Right, and we saw this on the front page. Right, I calculated the theoretical, which was 33%, and then the empirical, which was 16.7%. Right, that was way off, and that was because I only did the experiment 6 times. Whereas in example 4, yeah, I did the experiment 5,814 times, and so with that many times, it was pretty close. Okay. All right. Unusual. So what's considered unusual? So an event is said to be unusual okay, so in English, the word unusual means what? It means weird, rare, something that doesn't happen a lot. So something is unusual if it has a low probability. And I say low because what does low mean? So the most common criteria for low is 0.05. So if something has a probability that's less than 0.05, we consider that to be low, which is unusual. We consider that to be unusual. Okay, and 0.05 is the same thing as 5%. So if something has a less than 5% chance of happening, we consider that to be something that's unusual. Now, you have to be careful here because this 5% criteria, it's very situation dependent. So 5% just means 5 out of 100. Right? So we're talking about 5 out of 100 catches a certain disease. That's kind of low, right? 5 out of 100, that's not a lot. That's kind of low. If we're talking about, say, airplanes crashing, right? 5 out of 100 airplanes crashing. I don't know about you, but to me, that's kind of high. That's too high of a risk for me to get on a plane if you're saying 5 out of 100 planes crash. So it depends on the situation what's considered low. But 5% or 0.05 as a decimal is typically what you'll see most often as a criteria for something that's unusual. All right, that's all for today. Catch you in the next video.